Okay, then the next speaker is Professor Beatriz Ortega from EPHOOX Photonic Engineering.
So thanks, Pascual. Hello, everybody. Good afternoon. And welcome to EPHOOX Photonics Engineering presentation. EPHOOX is a recently founded startup company which was born at the Photonics Research Labs here at the Institute of Telecommunications and Multimedia Applications at the Politècnica University of Valencia. And as the slide says, we aim to be on the leading edge of microwave photonics technology. So this is just a quick overview of what I will be talking about during this talk. I want to present the company, and of course I want to talk about the technology we work about. And of course I'd like to present emerging applications which motivate us to work in this microwave photonics field. I will present several EPHOOX solutions we have, but mainly focusing on our flagship product, which is the Optical Vectorial Network Analyzer, and I will be describing it along my presentation. Well, I conclude my presentation with several examples of measurements we are able to do with our equipment. So with EPHOOX, what do we do? EPHOOX is a provider of innovative solutions based on microwave photonics technology, but not only for telecommunications sector, and also for other sectors like medical imaging, industrial processing, biomedical applications, and nanotechnology, etc. Our vision is to become an international leading company in the microwave photonics field. So, but let's talk about the technology. What is microwave photonics? Well, microwave photonics is a new discipline that combines technology developed for both the microwave and optical parts of the spectrum. Microwave photonic technologies enables the realization of any functionalities which is either difficult or even not possible in the electrical radio frequency domain. This discipline has attracted great attention during the last 30 years because of the new opportunities that create in the information and communication society. This technology, microwave photonics, was initially focused towards applications in the defense area, but recently it has been expanded to other civil applications, such as cellular, wireless, and satellite communications, cable television, or distributed antenna systems, also optical signal processing, optical packet switching, or medical imaging. So to understand the microwave photonic links basics, the best thing to do is to have a look to a traditional radio frequency approach. So in a traditional radio frequency approach, we have the radio frequency signal coming from an antenna or an optical signal generator, which is fed into electronic circuits where the processing tasks are being performed. So there we recover the electrical process signals and they go to new antennas or a given application. But the alternative which microwave photonics proposes for this signal processing, it employs the electrical radio frequency signal to modulate an optical carrier. The optical carrier is emitted by an optical source, by a laser mainly, and the optical modulated signal is directly processed in the optical domain. The optical processor is based on an optical core, which is mainly composed of fibers, fiber devices, or maybe photonic integrated circuits. And the process signal is recovered after photodetection, and the optoelectronic conversion is guaranteed, and electrical process signal is recovered at the endpoint of the microwave photonic link. Of course, you know about the advantages, about the wonderful advantages of the optical signal on the optical devices, and the large bandwidth, electromagnetic immunity, low losses, are guaranteed in this, yes, are guaranteed in the microwave photonic link because these advantages, which we all know about the photonic devices, are transferred to the electrical radio frequency signal processing. So this is our interest, and microphotonic, most of the microphotonic systems and links rely almost exclusively on discrete optoelectronic devices and fibers or fiber-based components. However, you know that these configurations are bulky and also power-consuming and lacks of flexibility. Furthermore, emerging applications and scenarios drive to size, weight, and power reduction, and also they need to implement reconfigurability and also flexibility. So there we get the integrated universal signal processor idea, which is a challenging approach inspired in FPGAs and software-defined radio to design a general-purpose programmable microwave photonic processor. It used to implement the main functionalities, but for that, we need to identify the suitable material to implement a single electro-optic platform, either on an specific application approach or as a universal processor, but of course guaranteeing the features above and also the radio standards. Well, it's very important to have in mind the emerging applications which motivate us to work in this field. First of all, I want to talk about 5G networks. The development or the deployment of 5G networks leads to a new paradigm for operators and also for manufacturers, because we find hybrid radio fiber access networks operating at high frequencies in the millimeter band and in a variety of scenarios, like shown in the slide, like in heterogeneous wireless access networks, also in radio over fiber access networks being compatible with WDM PONs networks and fiber backhaul and front haul. And well, that means the operators will need new test instrumentation and measurement instrumentation to perform diagnosis and characterization of the new hybrid radio over fiber links of the new convergent 5G fiber radio networks. So another interesting emerging applications are smart cities. Smart cities are born from the combination of information communication technologies such as cloud computing or enterprise systems, and different end user points which are transmitting or are reporting valuable information from the different points in an urban environment. We have examples in the traffic monitoring or lighting in the cities, describing the states of parking, energy stations. We have lots of examples in the information regarding different parameters in the cities, which is very valuable to understand and being able to process and transmit these cities always towards higher efficiency cities and reduce the consumption in power in the cities. And here we have another emerging application, which is the Internet of Things. It's a very important, interesting application which gives us upcoming services. The Internet of Things is the internet working of physical devices like vehicles, buildings, amongst others, all embedded with electronics, software, actuators, and sensors. And advanced connectivity must be guaranteed for the Internet of Things. Actually, experts say about the number of objects connected in the Internet of Things by 2020 would be 5 billion. So this is a huge amount of aggregated data which must be processed and transmitted. And this is a very interesting application because that will change the operability of our lives. Because, of course, power efficiency and other advantages can be obtained by all the management of such information regarding different aspects of our lives, like security, for instance, also energy, high-frequency radar for traffic, health monitoring, and there is such a big variety. I could be listing the hundreds of applications we can find around our lives, and which would be desirable to be able to process and have good use of them to improve our lives. Of course, all these applications can be improved by using radio over fiber technologies for transmitting these signals and associated microwave photonics technologies, which motivates us to work in our field. And here we have another application, the wearable devices. I'm sure that you get used to wear new watches to monitoring our sport activities, for instance, amongst others. Well, the wearable devices are able to collect information from human data, either for health purposes or just monitoring, but of course being compatible with the mobile network, and then being able for us to collect all this information to get our own statistics or for other purposes, such as reporting information to the health center, right? So I'm sure that it's very easy to understand. I'm sure you know that all the emerging applications I'm describing to you led to such a big aggregated volume of data that must be generated, transmitted, and processed. And I'm sure that it's very, very natural to understand that the role of photonics is crucial in this evolution of the networks. Now, the leading edge is to demonstrate, is to implement, is to deploy that microwave photonics technology is boosting all these applications and is going to facilitate the evolution and to boost new applications, new services for our upcoming networks. So there we find the role of EPHOOX company. So what kind of solutions does EPHOOX give us for this microwave photonics technology need in the evolution of such a big variety of services in the radio over fiber networks? Well, EPHOOX photonics engineering provide two types of solution, all in the advanced instrumentation based on microwave photonics. It provides both products and services. And amongst the products, I would like to emphasize on our flagship product, which is the optical module for the vectorial network analyzer. It also provides other components and peripherals, and the idea is to supply to the customer an integrated solution to a greater extent. So that's why we can supply other components which can be in combination, which can be operating in combination with our photonic solution. For instance, we have Genista, which is interested in supplying the lasers with our solution for a more integrated solution, as I said. Well, other services offered by EPHOOX are based on personalized products, as I will be talking about later on, and consulting services. So now I would like to talk with a little bit more of detail on the optical module for the vectorial network analyzer, and I would like to describe it. Here we have the instrumentation. It's an advanced photonic module which characterizes the S parameters of a variety of components and devices like electro-optic modulators, photodetectors, passive components, fiber links. And it expands the functionality of an electrical vectorial network analyzer because this photonic module allows to perform also measurements in the electro-optical, optoelectronical, or optical configurations, depending on the type of component we are going to characterize. Right? Measurements are performed with a large bandwidth, up to 67 GHz, and they can be done also in an extended range of optical wavelength. So up to now in the market, we only could find one integrated solution for doing this type of measurements, and only one provider supplied the corporate solution, including the electrical vectorial network analyzer and both the optical module. But there was no separate photonic module for this type of functions. Well, so this is the added value of our component. Our component is going to be compatible with any electrical vectorial network analyzer. Up to now, if the customer had a vectorial network analyzer in their labs, and they need to do these new measurements, which, as I talked about in the emerging applications, are going to be crucial for the development for next deployment of networks. So the need of this type of measures would require that the customer must buy another equipment, a whole equipment consisting of electrical and optical modules. Well, our solution is a good chance to avoid buying all the global instrument, because our photonic module is compatible with all the electrical vectorial network analyzer which you can find in the market. For instance, you have the Rode Schwarz, the Anritsu, and others which you can find in the market, and they are about over 90% of the market. And our module is compatible to those. So here you have the block diagram of our solution and the OBNA description. So there you have our photonic module is like an interface between the radio frequency electrical vectorial network analyzer and the device under test, right? So we can set our module under different configurations depending on the type of the measurement we want to do for a given device under test or a given component to be characterized. For instance, the schematic on the left corresponds to an optical measurement, and as you see, we take the electrical signal out in the output port from the electrical vectorial network analyzer, and this is modulating either an internal optical source or an external laser in the electro-optic converter stage. The optical modulated signal is launched into the device under test, and the output optical signal is going back to our photonic module, where the optoelectronic conversion is being held. There you have the electrical recovered output signal, which goes back to the electrical radio frequency vectorial network analyzer you have. This configuration corresponds, as I said, to an optical measurement, but you have other options depending on the type of on the component you are characterizing. You can also perform optoelectronic characterizations or electro-optic characterizations in different configuration stages. At the moment, both stages for electro-optic and optoelectronic converters are based on fiber and fiber devices and discrete components. But of course, I'm sure that integrated photonics will play a very interesting role in obtaining evolution of our stages at the moment to implement more compact and lower reduced cost and more compact solutions for our device, for our instrumentation module. So I believe that integrated photonics will play a definite role in the evolution of later versions of our product. So what is the added value of our product? Well, the added value is in terms of adaptability, the full compatibility with the vectorial network analyzer solutions, and also the upgradability of hardware and software of the equipment. Regarding the advanced functionalities, our instrumentation module allows to perform characterization in amplitude and delay of optical components in a variety of them, as I said, and also it reduces the uncertainty in the measurements. It also allows the time domain measurements. Regarding technical improvements, we demonstrate with our device parameters which have been significantly improved regarding other solutions in the market, the corporate one, as I said. In terms of relative uncertainty, we reduced it to 0.6 dBs, for instance, at 50 gigahertz, and we have extended the operation wavelength range. We have reduced the noise floor also at 50 gigahertz, and also we implement a protection for internal optical components in our module. And finally, there we get our device. Finally, as our philosophy in EPHOOX company is thinking of clients, we, of course, guarantee exceptional client care, excellent calibration, and first-rate repair services, and functional design and intuitive guide to operate with the module. Well, how to perform the measurements here? I'll talk very briefly, but here you have the configuration menu of the software, which is served with the component, our instrumentation. And then in the configuration menu, you are able to select the type of measurement you are going to do, the type of components you want to characterize. And in this sense, you are giving the parameters that will guide you along the software to facilitate how to perform the measurement. The measurement display shows measurements in terms of magnitudes against frequency. Here you have several traces there, but it's better if you look at the right in the slide. Then you have several examples of measurements. All the measurements correspond in magnitude to frequency response, and the one at the top represents an electro-optic measurement, which is the characterization of an electro-optic intensity modulator. The one in the middle, on the right, represents an optoelectronic measurement, which is the measurement of the responsivity of a photodiode. And at the bottom, you have an optical measurement corresponding to the characterization of a 20 kilometers analog dispersive fiber link. So optical measurements could be also employed to characterize any other type of optical device, such as optical amplifiers, optical WDM multiplexers, attenuators, couplers, and a passive device also. So as I said, as I described to you, and I showed to you the different schematics of blocks, so the configuration of electrical and optical cables are different depending on the type of the device you are performing, on the type of characterization you want to perform, electrical in the vectorial network analyzer, or any other option selecting optical in one of the output or input. So, and as to conclude, EPHOOX also personalizes the products. So if we have a customer that presents us the project, then different departments in EPHOOX are combined, are integrated to present a prototype. So designing, engineering, in the processing and the industrial engineering department would lead to a development of a prototype and then the final product. So the whole process is covered by EPHOOX company. And this is our intention for the next years. And which is the role of photonic integrated technologies in all of these? I have been telling you about that along the presentation, but I would like to recall you in the last slide of my presentation that I see that EPHOOX Photonics Engineering Company and the photonic integrated technologies are related by a double-sided relationship. This is because, on the one hand, I believe that photonic integrated technologies could allow us to develop further evolution of also for both the electro-optical and optoelectronic conversion stages within our photonic module developed in EPHOOX in terms of obtaining more compact, reduced losses, and reduced costs solution that will be in further evolutions of the product. But This is on the one hand, but on the other hand, I'm sure that EPHOOX provides solutions for you to measure any photonic integrated equipment or any photonic integrated circuit for any application, either if it is on the electro-optical side or on the optical-electrical side, and also in the optical behavior. For all these interesting applications or the upcoming services, I already showed to you along my presentation. So I hope we can collaborate in any occasion, because I see photonic integrated technologies and EPHOOX company could be strongly related in the future, in the next future. And finally, I will invite you to visit our web, ephoox.com, where you can read the application note of our flagship product, and also you can see about our solutions. And of course, I thank you very much for your attention.
Thank you, Beatriz. So now it's time for questions. Beatriz office is 2 doors at the side of mine, so I can ask her every single question I wish all along the year, but you cannot. So, yes, thank you.
A very short question.
Yes,
because I'm just curious about the behavior you showed us about your flagship product. Yeah. Those nice graphs that you plotted there about the characterization of different devices. Mm. And I was wondering, because I saw that you can measure S11, S21, S22, S12. I am wondering if you can do this, you can perform this measurement in the optical domain, or is in the electrical domain? I mean, are you able to characterize return losses or optical reflections, or it's just only the electrical ones that you find in the ports of, I don't know, the photodiode? Or?
Yes. Okay. If you want the analysis in terms of frequency, then you have to go back to electrical domain, because then the vectorial network analyzer is providing you the analysis in terms of frequency. Of course, you can do optical measurements, but then the signal will be analyzed in the electrical domain.
Thank you.
You're welcome.
Any other question? Okay.
Okay. So thank you very much for the invitation. Thank you.
So let's welcome last speaker for today's session, which is Pérez Millán. He comes from FILA and also a startup from Universitat de València. Welcome.
Okay, thank you very much. Thank you very much, Pascual, for your introduction. Well, first of all, I would like to thank the organizing committee for inviting me to this to give a talk in this frame. When Ruben phoned me to invite me to give a talk in Photonic Integration Week, my first reaction was that I was not the appropriate person to give a talk in photonic integration, because we at FILA we build fiber lasers, and we use optical fibers and optical fiber devices to build these lasers. So, but he reminded me that we had some applications in our website where we claimed that our supercontinuum sources were useful for applications where photonic integration has a lot to say. So he was right. Indeed, our supercontinuum lasers are an optimum source to characterize photonic integrated devices and circuits. And on the other hand, in the near future, supercontinuum technology will need to offer more compact devices, more compact versions to the market, since many sectors are blocking the entrance of supercontinuum technology because of its size, its weight, and its complexity. So probably photonic integration has an important role for this to be a reality, for manufacturers to be able to offer the market more compact supercontinuum sources. So this is why the title of this presentation, which is Perspectives of Photonic Integration in Supercontinuum Technology. The structure of the talk will then be as follows. I will briefly introduce Fila, who we are, what we do, what we sell, where we do sell, and what a couple of applications, of interesting applications that I want to stress out, which are those where we are entering with more success the market. Then I will move to explain why supercontinuum sources are optimum to characterize amplitude and phase properties of integrated photonic devices. Then I will summarize my vision, my opinion about how photonic integrated devices can help manufacturers as Fila to integrate, to make more compact supercontinuum sources. And finally, I will conclude. So, Fila is a company based in Valencia. We build fiber lasers. We have different types of lasers, but all based in fiber. And they emit in the ranges from continuous wave, nanosecond, picosecond, and femtosecond pulse widths. We are one of the very few companies in the world that are controlling the supply and manufacture of those devices that are composing our lasers. That's a big advantage. That's really one of our most competitive advantages, the fact that we manufacture our own key optical fibers. So we are, well, the central site is in Valencia, the R&D department also, and our factory is in Barcelona. We are currently selling our products all over the world. In the main countries in Europe, we have customers. We also have customers in Asia, Japan, China, Korea, and also in Latin America, in the main countries of Latin America, Brazil, Colombia, Mexico, and are now working into entering the United States market. So that's a brief summary of what we are and where we are. So one of our products is the supercontinuum laser. Supercontinuum laser is a white laser. The principle of how we generate a white light laser is, in principle, simple. It is just that we use a photonic crystal fiber with the proper dispersion and nonlinear properties to convert the wavelength of a conventional laser, which is monochromatic, into a white light laser. This is done thanks to those highly nonlinear properties of the photonic crystal fibers and the dispersion management of the manufacturing of these fibers. So we combine with a laser the properties of a lamp, which is this very high broadband emission, with the properties of a laser. We have a spatially coherent source with very high brightness and directionality. So what we have is a laser beam of white light. These combined properties offer unparalleled white light brightness. That means that the sensitivity of the measurements that we can do remotely of different samples is very high compared to other sources. It is very easy to integrate because optics are easy, and the access to that light is easy because directionality is kept throughout the whole optical path. And one important property of these lasers is that they require low power to emit very high brightness compared to their competitive technologies. So this, here you can see the different references that we have currently at FILA. These are two different types of supercontinuum lasers, the reference SC and the reference SCT. The SC reference is a laser which is a chaotic laser. It is emitting pulses chaotically with a repetition rate in the range from 30 to 50 kilohertz frequency, with pulses of several tens of nanoseconds. This is a very useful source, white light source, whenever you want to use high energy pulses. Applications requiring high energy pulses are applications where this laser is very useful. In the case that you need a very stable source and with a very high repetition rate, then what we offer is the SCT. It is a source that emits pulses at a frequency repetition rate which is fixed, and it is of 20 megahertz. Since it is based in mod-locked lasers, it is very stable, both in amplitude and phase. And it is useful for applications where you want to use it just as if it was a continuous wave white source, or applications where you need synchronization. Synchronization like lifetime fluorescence microscope measurements, for instance, where you need to synchronize your pump and your probe and see the lifetime fluorescence of a material, for instance. So whenever synchronization is required for your measure, then this is a very good solution for your system. Both are compatible with a tool that we also manufacture and sell, which is an accessory to tune the emission of that laser working as a filter. It allows the user to use each of our references, changing the central wavelength from, in this case, which is the reference for the visible range. You can move your central wavelength from 450 nanometers up to 850. And what is more important is that you can also change the line width or bandwidth of your emission, typically from 5 nanometers up to 300 nanometers. So I will stress out a couple of applications where microscopy, where the market is is understanding this technology and is buying our technology. One of them is confocal fluorescence microscopy. In these lasers, in these systems, advanced laser microscopy for super resolution imaging, confocal microscopy is used to take images from samples which are dyed with fluorescent components, with fluorescent fluorophores. Okay, so to take an image, you need to excite with a given wavelength where that fluorescent, where that fluorophore is sensitive. So to get a composition of an image with different fluorophores, you need a set of many lasers, many laser lines, each at a given wavelength. So this is the standard way to work with advanced laser confocal microscopy. It is clear that our supercontinuum source might be useful to eliminate the need of several laser lines with just using one single supercontinuum source and with using the arbitrary spectral filter that I told you before. This is something that one of our customers at ICFO has demonstrated with taking images with even with the same or even higher resolution than with standard laser boxes. These are some pictures of their setup. You can see here the conventional box of lasers that are feeding a standard confocal Nikon SC1. This is a setup that you can see how complex it is. You need different technologies indeed of lasers to have different lines from blue to red in their case. And it is all free space that has to be coupled to a single fiber. So the replacing of this set by a supercontinuum laser simplifies enormously the way of illuminating or feeding the microscope with white light. So just with a way of just with the system of selecting the bandwidth of and central wavelength of the emission, you can just, for instance, illuminate with green light or illuminate with red light that sample. That sample, in the case of red, will be dyed with a fluorophore sensitive to red, and in this case sensitive to green, just with a single source. And this is one of the examples of how is this setup performing. It is an example of cells of the type BSC1. The nucleus of those cells are being dyed by a fluorophore which is sensitive to 568 nanometers, and the microtubules of the cells are being sited by are being dyed by a fluorophore sensitive to 647 nanometers. These are images of different planes of the sample, and in this technique, what the researchers do is to differentiate different components of the cell and then make a combined image. The result is a very high resolution image below 1 micrometers with very well differentiated components of the cell. What is very interesting and of which we are very satisfied is the fact that the parameters, the standard parameters of the confocal microscopy are the same that are being used, or even better in the case of using a supercontinuum source with regard to a set of laser lines. We are taking images at a 1 second frame rate and with gain of the photodetectors in the low range of a value of 30 compared to a maximum of 256. So it is completely comparable to the more standard technical way and technical approach, and even better in some of the applications. Moreover, this laser has been used to make in vivo imaging. Here, what you are seeing is a sequence of images of a type of cell that has a axonal growth behavior. It is a type of cell that is used by researchers to simulate tumoral neurons, how those tumors are being grown. What is very satisfactory of these images is that this image has been taken, well, it is just a sequence of images of a measurement of 30 minutes, and the image is of very high quality with very high resolution and without different values of the power obtained. So that is possible thanks to the stability of that laser source. Another application is food sorting. I won't go deep on this application, but the idea is that you can use a supercontinuum laser to take the spectrum remotely of a given food sample. If that spectrum is correct, if that spectrum, then the sample passes the quality test. If it is not correct, if the spectrum indicates that sample is not healthy, then the machine eliminates that sample. So it is a food sorting machine. These machines of one of our customers has been able to work at a sorting rate of 6 tons per hour using one supercontinuum laser. Okay, so once I have just gave you a couple of insights of our applications, I will explain why supercontinuum sources are optimal for photonic integrated devices characterization in the optical domain. Well, what are the advantages? Well, so since the light is generated already in the single mode core of a fiber, you get typically spectral power densities over 40 dBs compared to other light sources that has to be coupled to the light that to the fiber that is being used to